Okay, this lecture 21, I want to talk about negative refraction. So there won't be any homework assignments on this, and we're not going to go into any great detail on it, but just because it's an area of current interest and active research since about the year 2000 is when it kind of emerged on the scene, though its origins date back to a paper from the late 60s from a Russian physicist by the name of Veselago. It was revived by physicist at Imperial College London, John Pendry, around the year 2000. And we saw a lot happening in the 2000s, and there's still stuff going on with it today, and it's interesting, and I just happen to have worked on some of the theory behind this stuff. One of the papers I have out there is called The Physical Origins of Negative Refraction. So let me just mention negative refraction briefly. So what is it exactly? And in simplest terms, or at least in terms that we can understand, if I consider a material N1, right, which I'm going to denote as positive, right, and then I want to have N2, but I'm going to write the index of refraction as negative, okay, which seems kind of funny, right? What exactly does that mean? Well, as it turns out, one thing that it means is that, I don't know why I can't draw straight dotted lines. One thing that it means is that if we come in with a ray at some angle of incidence, that it'll still kind of bend towards the normal, but the weird thing is that instead of bending on this side, it bends on this side. So refraction occurs on the other side of the normal, right? And that should be, very jarring and alarming to any physicist, because you can see that this has got, there's a continuity in the y direction. It's got a velocity in the y direction, and it continues to say, I guess this would be negative y velocity, right? It continues to be negative y velocity inside the material. But the x velocity, right, is in the positive x direction, but once we're in the material, it's in the negative x direction. So there's your kind of negative index of refraction notion, right? It's because the velocity in this direction is now negative. So it bends to the other side of the normal. And, yes, that's weird. Why would it be useful or interesting? And I'll give you some idea about that in a moment. I'm not going to go into trying to explain why this is. I'm not even going to reproduce the least time principle proof of this, or demonstration of this, that it would happen this way if the index was negative. You can do it. You can do it using the least time principle. And I'm not going to talk about what the physical origins of it are, because that is mired in ideas that you aren't familiar with yet, namely the permittivity and permeability of materials. But what I will say is some interesting aspects of it. It was reintroduced on the scene by John Pendry when he wrote a paper, I believe it was titled How to Make a Perfect Lens. Okay? And for reasons that you need wave optics to understand, when you image things with lenses, there's a resolution limit to how fine a point you can focus to, which turns out to be in, like, when you try to use it as a magnifying glass, how small a thing you can see. And so attempts to get better resolution in imaging were something that people were interested in, and still are. So this idea there, right, if we have a negative refractive material, let's just say we have a block of it like this, and let's consider a couple of rays, right? So we're like imaging something from over here, right? And we'd have the diverging lines like this, right? But what does it do inside the refractive material? Well, since it bends, actually it would be the other way around, sorry. If we came in with a ray, did I just do the same thing? Yes, I did. Get a couple of rays like this, right? So they're going to get to this junction. Instead of bending on this side, they'll bend on this side. Instead of bending on this side, they'll bend on this side. You see? So they have a kind of a focusing property, right? Since they oppose the angle of the ray, right? And so you can think of the slab of this negative refractive material as being able to form some kind of lens, right? And so that was the idea there. They're trying to make lenses out of it. The other thing I'll talk about, which was of great interest to me, so I worked with an engineer at Purdue by the name of Kevin Webb, and we had an idea that we were floating around trying to get some traction for and some funding for, which was this idea of basically creating an invisibility cloak, right? Like in Harry Potter, he puts the cloak on, but really more like Predator, if you've seen the movie Predator, right? The way that he's invisible is the way that we imagined these negative index materials would work. And so if you can bend light in this funny way, you might be able to bend light around an object, right? Because if I imagine that I have an object, like a man in a field, for example, right? And, how does someone over here see him? Well, he sees him because a ray, right, comes from the man to this man's eye, right? Well, what if you could find a way, let's say that in the background here we've got, a tree. It's a terrible tree, but I can draw a better tree than that. There we go. That's a nice looking tree. Happy little trees. Okay. Instead of this man seeing this man, what if we could find a way to make light bend around? If you could do that, right, and then let's consider other rays, like say this one here, bend around the man here. Yes? If we could find a way to make light bend around an object, then we can hide the object, right? And so negative refractive material seems to offer, in theory anyways, a way to do this. Now the realities of how to make the materials to do it, well, that's something that only continued research and a variety of different fields, right, will eventually, find a way to do it. I had proposed something that used ferroelectric and ferromagnetic materials. You have to make some kind of composite material out of the two so that you had a negative permittivity and a negative permeability to get stuff to do this in the near infrared. But other things you could think of, hiding airplanes, right? This is the ultimate kind of stealth device. And so we've investigated what would the ramifications on what's called radar cross-section. That's how big an object appears, right, to a radar. You can see big things, can't see small things. Like a stealth bomber is a big plane, but has a radar cross-section probably on the order of like a BB, right? It's pretty small. And so what would negative refractive materials offer for that, right? That was an area of interest. But the invisibility cloak thing, right, was something that we really thought was a cool idea. And we had, even laid out, the basic ideas behind the theory. We had already done some stuff on perfect lenses and diffraction limit and things like that as it pertained to negative refraction, as well as my theoretical work on the physical origins of negative refraction. And so we were very excited. We had this great presentation. We knew we were going to get tons and tons of money from the Department of Defense and Air Force and people like that. And then we got scooped by Pendry and another guy. I can't remember the other guy's name, so Schultz or something like that. But yeah, and so we were trying to put together this big team. And had this mathematician who had just won the MacArthur Prize. He was, this great genius, and so we were trying to get him involved in the project. And yeah, and then we got scooped.
Does that mean they stole your idea?
No, I didn't steal it. Of course not. When we all knew each other. You're at conferences, you're talking, and ideas bounce around. And if everyone kind of hears the same inputs, at some point they're going to, arrive at similar conclusions. And so it shouldn't be surprising that the kind of things that we were talking about at these conferences would result in the idea of, invisibility cloaking, or what I call light, object obfuscation. It was more than just invisibility cloak. I also was talking about, the idea of, creating the appearance of, an army on the horizon. It's like a mirage almost, right? To scare off your enemy, like the 1991 war in Kuwait, where the Republican Guard. They knew the army was coming across the desert, but they believed falsely that the Marines were invading from the sea when they were not. It was just a mirage of sorts. So, yeah, no, nobody stole anything. They just got to it first. But I didn't think, I thought it was a harebrained idea, and I thought nobody would, really have the courage to go out there and say, hey, we want to make an invisibility cloak like in Harry Potter or Predator. So I thought we were safe, and I guess if I had known that we would get scooped, then I'd work faster, but is what it is. But very exciting times, at least for me. It was a cool area to work in, and so that, loosely relates to what we were talking about before, Snell's law and refraction and the least time principle. So I just wanted to mention it, and that's all I'm going to say on that.